Okay, we're going to do a little block of work on correlation, and then we're going to follow that up by something closely related called regression. Now, correlation and regression are the one bit of the course where we deal with what we call bivariate data. And bivariate data means that for each individual in the population, it might be a magpie, or for at least each magpie that's in my sample, I record more than one item. In fact, two. That's what the bi means in bivariate. There are two measurements we take of each magpie. So maybe its wingspan and its weight. And I could then plot both of these things, okay, on the same graph. So I might have wingspan on one axis and weight on the other. Now, when we come to do regression, it may matter which way around these two measurements are. But for correlation, we're just seeing, do large wingspans tend to go with large weights? I mean, I may get a pattern like this. So here, each cross is a magpie in my sample. Okay, and it does seem to be the case that the magpies with bigger wingspans did tend to have higher weights as well. Okay, it's not a precise measurement. This is statistical data. So here we've got a magpie with a considerably bigger wingspan than this one, but it's got a smaller weight. But generally the pattern is upwards. Now, the correlation coefficient that we're going to be using, which is called Pearson's, or it's sometimes called the product moment correlation coefficient, Pearson's correlation coefficient is based on the idea that it will tell us whether the data seems to be clustered around a straight line. Okay, now finding the equation of that line is what regression is all about. But it's only suitable for linear models. So this straight line looks reasonable, but if I've got more x's, it might be that this relationship is actually a curve. There's not enough data to suggest that here. But if there's any indication that the data forms a curve, then Pearson's product moment correlation coefficient is not what you want. Okay. The other thing you've got to watch out for is that it does not tell you anything about causation. So it would be a bit silly to say that the magpies weighed more because they had a big wingspan. It's much more likely that they've got a big wingspan and a big weight simply because it's just a bigger magpie. So you've really got to watch out for any idea about causation. I mean, think about this one. So I have 20 towns, and I've recorded how many dentists in each town and the number of knife crimes there were in 2016 in those towns. And look, I get a very pronounced positive correlation. Okay, we'll show how Pearson's correlation coefficient will actually tell me that in a minute. Okay, but do I really believe that the number of dentists are causing all of this knife crime? Is dentists to blame for the knife crime? I don't think so. I think that these towns here are small towns, so they don't have much knife crime, they don't have many dentists. These towns here are big towns, so they have lots of dentists and they tend to have more knife crime. So you've got to watch out. Just because there's a correlation doesn't prove that there's any causation. Okay, so for both of the diagrams I've drawn so far, there's quite a strong positive correlation, maybe slightly stronger in this one than this one. I would estimate that R, so the letter R is the letter we use for Pearson's correlation coefficient. I would reckon that R would be about 0.85, 0.9 for this one, and maybe R equals 0.75 for that one. So you're supposed to be able to get a visual impression of how strong the correlation is. Correlation, of course, doesn't have to be positive. It could be that one of my variables increases, the other one decreases. So this pattern here would be negative correlation. Okay, so it could be that the more crime there is in a location, the fewer people want to live there. So as crime goes up, the number of people looking for housing in that area goes down. So you can think of all kinds of reasons why you might have a negative correlation rather than a positive one. Something like this would be, well, you may be able to see some correlation in those crosses. I can't. Okay. Typically, if R is something like, maybe this is minus 0.1, just maybe slightly they're a better fit to a line sloping downwards than a line sloping upwards. But a correlation coefficient, between about minus 0.3 and 0.3 is just not worth worrying about. It's too small to be of interest. So here's one exam board's guidelines. It's the board we used to use and we haven't got any guidelines from the current board. So these are just a guideline, but they're useful. So if you've got a correlation of stronger than 0.9, then this is very, very strong. You could even say it's almost exact. 0.7 to 0.9 is strong. Anything between 0.3 and 0.7 is less impressive. Okay, but there's some correlation there. So you could say moderate or some correlation. Anything less than 0.3 we're not really very impressed by at all. So you can say almost no positive correlation, or even almost no correlation. It's certainly very weak, whatever it is. And certainly below 0.1, you're not going to say anything. Obviously, these are the positive values, and you can make similar comments about negative ones. And what you can see to that is there is an upper limit to R. You can get an R of 1. So an R of 1, R equals 1, the points would be exactly on an upward sloping straight line, and R equals -1 would be when the points are on an exactly downward slope, or exactly on a downward sloping straight line. Doesn't matter what the gradient of the line is. If it's an exactly horizontal straight line, then one of the variables isn't changing at all, and you'd probably get an error if you tried to work out what R was for that. But if the line slopes up or down and it's a perfect line, you'll get a value of 1 or -1. There is no way you can possibly get a value of R that's bigger than 1 or less than -1. So if you get one of those, then it is a mistake. So that's an overview of what correlation is.